In our earlier classes, we were discussing about stresses in the soil, and we have also talked about flow through the soil. Okay. So when we were trying to talk about flow through the soil, so where we were referring to only one directional flow, either a vertical directional flow or a horizontal directional flow. So only for a particular one-dimensional flow, we were trying to talk about how the flow is trying to happen through the soil sample. Now, what is this seepage all about? Seepage is nothing but it's once again the flow through the interconnected void path only. Okay. So because of the total head difference between upstream to downstream, the flow is happening through the interconnected void path. Now, what specifically we are going to be focusing here is we are going to be dealing with the problems which are related to that of the two-dimensional. That means in a plane, if the flow is taking place. Okay, I repeat. So in a plane, if the flow is taking place through the soil sample, so how much is that quantity of flow happening, or rather how much is that seepage taking place from upstream to downstream in the two-dimensional space? That is what we are going to be talking about basically in this particular next couple of lectures. So yeah, as I told you, like the earlier discussions that we had in which we were trying to talk about flow rate or rate of flow or discharge happening in a one direction, particular direction, maybe horizontal or vertical or in some inclined direction, but it's particularly in one direction. Okay. Yeah. So even in that one directional or one dimensional flow condition, what we were trying to understand is how much is that total head difference between upstream to downstream, and how to calculate the total head at the upstream, how to calculate the total head at the downstream. And because of that total head difference between upstream to downstream, so we understood that the flow is going to be happening through the soil sample. But when it comes to the reality, we are not going to be mostly coming across with what is only called as your one-dimensional flow happening through your soil. Okay. So what most commonly you will be coming across is the flow happening in two-dimensional space, or what we will be talking about is a two-dimensional flow. So in reality, the flow of water through soil is not in a one direction only. So rather we are going to be having what is called as the flow taking place in two-dimensional space, and nor it is a uniform flow over the entire area of cross section which is perpendicular to the flow. What we have assumed earlier is the flow whatever is happening through the soil which is perpendicular to the cross section. If I say this is my cross section of the soil, the direction of the flow we consider it to be perpendicular to the direction perpendicular to the cross section of the soil sample. Okay. So once we say the flow what is taking place perpendicular to the cross section of the soil sample, we assume that it is to be uniform over the complete entire area, but it's not going to be exactly the uniform condition of flow happening over the complete cross sectional area. Rather, some place you might have more amount of flow taking place through the interconnected void path. At some other cross section, you might have less quantity of seepage happening through the interconnected void path. But however, we assume that it's more or less a uniform flow which relates to that of a steady state condition. Yeah. So typically when it comes to the case of what is called as your two-dimensional flow, okay, you could clearly see that this is my upstream, this is the downstream, and the flow is happening when the water is trying to flow through the soil sample. The flow is expected to be happening through the soil from upstream to that of your downstream. Okay. Now, whatever this particular lines that you could see here, these lines are nothing but we call them as your flow lines. I repeat, these particular lines, whatever we could see here, is nothing but we call them as flow lines. I'll be trying to talk about regarding this little more in detail so that you get a clarity on what is that this flow line and other subsequent things which I'll be trying to talk about. So in the case of this two-dimensional flow, when why I'm trying to talk about this two-dimensional flow in the sense, in any kind of problems that we try to deal with, maybe in the case of earthen embankment, or maybe in the case of a concrete dam, or maybe in the case of, let's say for example, this case, what we are looking at is nothing but it is a sheet pile. This is nothing but, this vertical member is nothing but we call it as a sheet pile. What is this sheet pile trying to do? It is trying to prevent the flow happening from upstream to downstream. And as this particular sheet pile, which is considered to be impermeable, so flow is not directly happening across the cross section of this particular sheet pile. So how is that flow happening? The water is trying to move from upstream to the downstream from the bottom of the sheet pile only. Only from this much cross-sectional area of the soil strata, only through this cross-sectional area of the soil strata, the flow is trying to happen. Now, because of the introduction of this sheet pile, what is that advantage we had means we are trying to minimize your seepage losses that are going to be happening from upstream to that of your downstream. Why is that how come you say that your seepage losses are minimized? Because the flow, whatever we are trying to talk about, as it cannot happen through across the cross section of this sheet pile, as this flow condition is not allowed to happen, as the sheet pile is driven over certain depth into the soil strata. So over this much depth of the soil strata, over this much cross section depth of the soil strata, your flow is not happening directly from upstream to downstream. Rather, flow has to happen only from the bottom of the sheet pile, through which your soil medium, which is considered to be porous, so only through that particular region of the soil medium, your flow can happen through the soil. Now, why is that we are referring to a two-dimensional flow here? Because if a water particle that I am looking at here, if it has to move from upstream to downstream, how is it traveling? It is, so to some extent it is traveling in the vertical direction, to some extent it is traveling in the horizontal direction, and then it is subsequently traveling in the vertical direction to get out on the downstream side. So in order to have your water particle to seep through the soil sample and move from upstream to downstream, the water particle is not particularly traveling only in vertical direction, nor only particularly in horizontal direction. Rather, you could see that your flow is going to be happening through the soil sample relatively both in vertical, I can say a combination of both vertical as well as your horizontal direction. Sir, why not in the third direction? So most of the times in the case of geotechnical engineering, this direction we consider as your x-axis. This vertical is what we consider as z-axis, and this particular axis, rather in this direction, we consider it as your y-axis. Okay, so this is nothing but z. Vertical is your z, horizontal is your x, perpendicular to my board or laptop is nothing but it is my y-axis. Sir, why is that you are specifically saying your water particle will flow only in two direction? Why not the third direction? Why is that water particle not traveling in the third direction? Because water particle is free to move in any direction. Why is it not happening? Why is that flow not happening in the third direction? Whenever we come across with any hydraulic structure, what generally we see is that in the direction perpendicular to this board or perpendicular to the laptop, what we see is that the length of that cross section is relatively long. Maybe length of your embankment or maybe length of your concrete dam, what we are trying to talk about, is relatively long. So that's the reason why the flow of a water particle, in order to move from upstream to downstream, will happily happen through the cross section, across the cross section of your structure, but not along the length of the structure. Because if the water particle is trying to travel along the length of the structure, what would happen? The water particle still remains on the upstream only. It cannot go on to the downstream. If the water particle is trying to travel in this y direction, so water particle still remains to be on the upstream side only. It cannot go on to the downstream side. So that's the reason why we say most of the cases of flow conditions, whatever we try to talk about, we consider it to be simply a two-dimensional flow condition. But whenever we come across with the case of what is called as compressibility taking place in the soil, that's nothing but the case of consolidation which is taking place in the soil. So there it's nothing but what we consider as water particle getting dissipated or water particle flow movement in the soil sample is relative to that of a two-dimensional flow, because the particle is free to get displaced in any direction, ultimately to get drained out of the soil sample. So in that particular case, we do even talk about your three-dimensional flow or the water particle displacement happening in any of the three respective directions. But when it comes to the case of your hydraulic structures, or flow calculations or seepage calculations, okay, so in all such cases, we generally consider what is called as your two-dimensional flow problem. This is typically another kind of structure what we have here. Okay, this structure is nothing but a concrete dam. So we have some storage on the upstream. This is the water storage on the upstream, and this is the water storage on the downstream. This is your soil strata. what we are trying to look at. And your concrete structure bottom is something like this. This part, whatever you could see here in the coarser representation, this is called as your filtering medium, or we call it as filter. Now, the purpose of this filter is to ensure that whatever water that is trying to seep from upstream to downstream, if it is directly getting dissipated on the downstream side, if the water particles are directly moving on to the downstream, we are going to see a problem what is called as piping failure, which I'll be trying to talk about maybe in the next class. Okay. So what is going to happen here is, as I have earlier discussed also, along with your water particle which is trying to get dissipated out of the soil sample when it is moving from upstream to downstream. So because of the movement of your water particle as the seepage is happening through the interconnected void path, along that water particle movement, if there are some fine grained particles which are coming into picture along the flow region, so those fine grained particles also sometimes gets carried away along with your water particle. Now, in such cases, when fine grained particles are also getting carried away with your water particle, after some point of time, the size of the interconnected void path keeps on increases, and you are going to see a large void cross-sectional shape which is getting formed as similar to that of a pipe inside your ground or inside your soil strata, because of the displacement or because of the escaping of your soil grains from that particular soil medium along with the seepage what is happening through the soil strata. So in order to avoid that kind of problems, and also in order to minimize your seepage pressure being developed at the bottom of your cross section of the structure, so we try to provide what is called as a proper filter design. We try to go for a proper filter design so that now whatever water that wanted to move from upstream to downstream because of the seepage will flow into this particular drainage path, and from this drainage path water can be collected easily, or water can be easily diverted onto the downstream without having any kind of failure in the ground, or rather without having any kind of failure getting transferred onto your structure. Now this, a combination of lines whatever are shown here, is nothing but this graphical representation of what is being shown. Okay, so you could see some lines. Yeah, this is one line, this is another line, this is another line, and these are some set of lines. Okay, similarly these dotted lines whatever you could see here, these are another set of lines. Okay, so now you have two different set of lines which are represented in this particular representation. Okay, so this representation of two system of lines is what we call it as a flow net diagram. Basically, the purpose of this flow net diagram is to calculate how much is the flow rate or how much is the seepage happening, because based on this particular flow net diagram, we will be able to estimate how much quantity of flow is happening from upstream to downstream across the cross section of your structure, or how much quantity of flow is happening across a sheet pile, or maybe how much flow is taking place across a concrete dam or an earthen embankment. So wherever it is, if you are dealing with seepage related problems, there we can try to calculate the quantity of seepage happening from upstream to downstream based on this what is called as a flow net diagram. Whereas this flow net diagram is basically a graphical approach by which you are going to estimate the quantity of seepage happening from upstream to downstream. Sir, is that only approach by which I can try to find out or get the solution from for the problem that I am dealing with? No, we have got a number of varieties of solutions for this particular problem. Okay, but I'll just try to discuss what are those different varieties, and out of all those different varieties, which particular approach by which we are going to solve our problems as of this course is concerned, we'll try to look at it. But try to understand that whatever this diagram that we could see here is nothing but we call it as flow net diagram. This part of the representation of lines. Okay, so this representation of lines is what we call it as a flow net diagram. Okay, earlier the flow of water for simple one-dimensional case is being calculated through direct application of Darcy's law. Based on simple Darcy's law, we were trying to estimate how much is the flow rate with which the flow is happening, or how much discharge is happening, or how much seepage is happening. So all such cases we have tried to deal with based on the simple conditions what we were trying to look at from your permeability test. Okay. Next, as it's not just only the case of one-dimensional flow conditions are what we will be coming across. So what mostly we'll be dealing in the case of hydrodynamic problems or hydrology related problems is mostly with respect to that of the two-dimensional flows. So it is very important for us to understand how to calculate your seepage for a two-dimensional flow conditions. So as engineers, we will wish to examine and calculate the leakage below the sheet pile or through or beneath the dam, which can be an earthen dam or maybe a concrete dam. So, and also to find how is your pore water pressure distribution existing at the bottom of your structure or maybe within the soil also at different places. And we might be interested in calculating how the effective stresses in the soil are at different places in the cross section of the soil, how they are varying. We'll be very interested in finding out. So that in all such kind of hydraulic problems, so we may not be directly dealing only by what is called as your one-dimensional analysis. So we'll be coming across with what is called as a two-dimensional analysis for calculating your flow condition. If the structure what we are trying to deal with is a sheet pile or a dam or whatever it is, which is relatively very long, that means the length of that structure is relatively very long. So what we do is we may neglect the component of the flow in the third direction or third dimension, as I have already told you, and we'll be considering the flow to be taking place through a slice of what is called as a unit thickness. So are we neglecting the third direction? Not exactly that we are neglecting the third direction. Rather, instead of looking at the complete length of that dam or complete length of the sheet pile, okay, what we do is for every 1 meter length of that sheet pile, for that 1 meter length of the sheet pile, we'll try to calculate how much is the flow happening from the bottom of the sheet pile or through the cross section of your earthen embankment or from the bottom of your concrete dam. So whatever is the problem, so accordingly we'll be trying to deal with it. So this corresponds to plane or in plane in the sense in a particular plane, the flow is what is being analyzed, which we also consider it as your two-dimensional flow condition. If pore water pressure, PWP refers to what is called as pore water pressure. Okay. So if pore water pressure varies with time, the flow will be time dependent. In general, what happens is that the pore water pressure, whatever gets developed in the case of consolidation related problems. Consolidation related problems means you'll have some external loading which is trying to, let's say I have a sponge which has some void spaces which are completely filled with water. If that sponge, I'm trying to apply some force on it to squeeze it. So what is that I'm going to see? If I'm trying to squeeze the sponge through the interconnected void path, the water particle starts coming out. So as the water particles are slowly moving out of your sponge or in similar lines in the soil, if the water particles are slowly getting dissipated out, subsequently what we would see is your pore water pressures which are building up in the soil sample will start slightly decreasing as the dissipation of water is happening from the soil. If this dissipation of water is happening from the soil where you indicate that the pore water pressures are varying with the time, then we cannot call that particular problem as a steady state problem. The flow, whatever we are trying to deal with, we cannot consider it to be a steady state flow, because what does the steady state flow says? The total head difference between upstream to downstream is always constant, and the flow what is happening through your soil from upstream to downstream is going to be because of the constant total head difference what you have between the upstream to that of your downstream. Okay, so the flow condition according to which we were trying to calculate your seepage or the discharge or maybe your flow rate, all that calculations were for the consideration of what is called as your steady state flow. Okay, so whenever we consider what is called as your pore water pressure variation, if pore water pressure variation is considered with the time, the flow what we are going to be dealing with cannot be considered as what is called as a steady state flow, as if the pore water pressure is varying with time, then what we need to be calling this as non-steady state flow, or we also call it as your transient flow. Transient flow in the sense the flow condition is not same at different intervals of time, rather the flow condition is changing with the time. So such kind of flow condition is what we call it as non-steady state, or we also call it as transient seepage. Such kind of seepage, what is happening to the soil is nothing but we call it as transient seepage. So that can happen. When do we come across with this non-steady state flow or transient seepage conditions? Whenever we have got an external cause like change in the head difference between inlet to that of your outlet due to any reason. Okay, so if the total head difference between upstream to downstream is not constant, in such case we come across with this what is called as your non-steady state. Why is that non-steady state coming into picture when the total head difference is not constant? If the total head difference is not constant, then your hydraulic gradient what you calculate is not going to be constant. If the hydraulic gradient is not going to be constant, then automatically the rate of flow what you calculate is also not going to be constant. If the rate of flow is not constant, you cannot say the amount of flow happening from upstream to downstream is no more going to be constant. So that's the reason why we say that particular flow condition to be non-steady state flow condition. And the other reason when you might come across with what is called as a non-steady state flow is whenever there is an internal deformation happening in the soil due to the during the process of the seepage. Okay, so whenever the seepage is taking place through the interconnected void path, if the volume of the soil is getting changed, if the compression or the deformation is taking place in the soil, then also we see that pore water pressure is not going to be constant with the time. So in such case, the corresponding flow what is happening through the interconnected void path is to be called as your non-steady state condition. This is one of that case. Okay, the other case is in the second case, there is a complex interrelationships between pore water pressure, seepage, and deformation, which basically a time dependent process, which we'll be trying to talk about in the next unit. That is nothing but in the consolidation, as I told you earlier. So where the deformation is happening in the soil sample, so because of the deformation happening in the soil sample, we are not going to be seeing a steady state condition existing there, rather a non-steady state condition which would prevail, because the pore water pressures building up in the soil sample are not going to be constant throughout at any point of time. So it is going to be changing with time. So pore water pressures initially will be increasing, and as the water particle starts getting dissipated out of the soil sample, so you are going to see the decrease in pore water pressures. If there is a decrease in pore water pressure, why did the decrease in pore water pressure happen? Because the water particle dissipated out of the void space. As the water particle dissipated out of the void space, now due to the external loading what is acting on the soil sample, so you are going to see the compression happening in the soil because the dissipation of water particle. So such phenomena is what we call it as your consolidation. So which is happening because of the deformation or the compression happening in your soil, which we will be trying to talk in the next class. Next unit, in fact. If pore water pressure, in case if the pore water pressure, what we are trying to look at, do not vary with time, then what we see is that the rate of flow, what is going to be happening, the amount of flow that happens to flow from upstream to downstream. So it's going to be remaining constant at any point of time for every interval of time. If you are looking at, let's say, for first 5 minutes or for next 5 minutes or for next 5 minutes, if I am going to understand how much is the discharge happening from upstream to downstream due to the flow, or how much is the flow rate happening with which the flow is taking place from upstream to downstream, or how much quantity of seepage is happening through the interconnected void path from upstream to downstream, so that is going to be constant. Okay, so that is all going to happen whenever your pore water pressure is not varying with time. So such condition is what we call it as your steady state flow condition. That is what I was trying to tell you earlier. If the pore water pressure is varying with the time, then we would say that your type of flow what we are going to be coming across is what is considered to be your non-steady state flow. If the flow rate with which the flow is happening in the soil is considered to be constant, then automatically we call that to be your steady state flow. If the flow rate is constant, which indicates that there is no variation in the pore water pressure, then we call it as a steady state flow. Or the subsequent seepage what is happening is what is called as a steady state seepage. Now, during the steady state seepage, your pore water pressure remains constant and no soil deformation is taking place. Hence, we will consider a two-dimensional steady state seepage, or we consider this particular seepage problems where we are not taking into consideration of the variation of pore water pressures. So such problem what we are going to be looking at is what we consider as your two-dimensional steady state seepage problems. The soil may therefore be regarded as rigid. Why do we say rigid? There is no internal deformation happening in the soil, so there is no change in volume of the soil. So when there is no change in the material volume of the material, so we consider that material to be rigid. Okay, so it's an assumption. It's not guaranteed that no soil has to be rigid, because when there is a flow condition existing, when there is some external loading existing, so it's not guaranteed that the deformation is not going to happen. Yes, deformation would happen, but however, we are not taking into consideration of that effect. The soil may therefore be regarded as rigid and stationary with a flow to be existing or taking place at a steady state condition. And also in this particular course, we will only consider the sample case of confined flow. We are not going to be looking at the problems which are related to that of your unconfined flow. What is that confined flow means? The seepage is going to be happening between two impervious surfaces, between two impervious regions only your flow condition is existing. Okay, so where the seepage, whatever we are going to be talking about, is confined between two impervious surfaces. Now, what conditions are to be satisfied in order to say that particular flow what is taking place is a steady state flow? Means the soil has to be fully saturated. Okay, then only we say the subsequent flow what is happening through the soil, the subsequent flow condition what is prevailing there is nothing but we call it as a steady state flow. Soil has to be fully saturated. The pressure gradient is unchanging. So what does this pressure gradient unchanging means? There should not be any change in what is called as a total head between upstream to downstream. So that total head difference should not be changing. When do we say total head difference is not going to change? Because elevation head will not change with the time. A chosen point on the upstream, chosen point on the downstream, the positions of this chosen points will not change. That means elevation heads are not going to change. So what are expected to get changed means your pressure head. So pressure head would change whenever your total head on the upstream is getting changed and total head on the downstream is getting changed. So whenever those total head difference between upstream to downstream is getting changed, we say that your pressure difference between your upstream to downstream or any 2 points what you are considering is also going to get changed. Okay, but however, we consider that pressure gradient or change in pressure, pore water pressures between 2 points, or maybe your change in your total head values between 2 points are considered to be not changing at all. Next is soil mass is constant. So in the sense, the mass of the soil across which the flow is taking place is considered to be constant. There is no additional water getting occupied into the void space, or there is no additional water going out of the voids of the soil mass. So which indicates that there is no change in mass of the soil there. The flow rate, or the rate with which the flow is taking place through the cross section of the soil, is also considered to be constant. Next. The problems what we are going to be coming across in this hydrodynamics are hydrology related structures. Okay, the hydrodynamic steady state fluid flow through porous medium follows the same basic laws as similar to that of the cases what we come across in the heat flow conditions or in the current flow conditions. If you look at heat flow, let's say the law of thermodynamics from which we can understand there is a heat transfer happening from higher gradient to that of your lower gradient. Okay, so higher temperature to that of the lower temperature, the heat flow takes place. And similarly, current flow also, from higher potential to that of your lower potential, the current flow is going to be taking place. In similar way, here the hydraulic flow what we are trying to talk about will also be happening in the similar manner from what is called as your higher head value to that of your lower head value. The way how we are going to deal with your heat transfer problems are current related problems, the current flow related problems. So in similar way, our hydraulic flow related problems are also going to be addressed based on what is called as your Laplace equation. Basically, your heat flow or current flow from maybe from your electrical engineering course, or what we learn from your thermodynamics course. Okay, so the way how those problems are analyzed, heat flow problem or maybe a current flow problem, how those problems are analyzed. In the same way, here also hydrology related, that's a hydraulic flow condition problems are also going to be analyzed. Basically, those flow problems are going to be analyzed by what is called as your Laplace equation. Okay, so we are going to look at how to get a Laplace equation for this particular two-dimensional flow condition, and by solving that Laplace equation, we try to understand how much is that flow happening through the cross section of the structure, maybe a hydraulic structure what we are looking at, or from the bottom of the hydraulic structure, and we try to understand what is the quantity of seepage or quantity of flow rate with which the flow is taking place in that particular problem. In flow problems, the Laplace equation is the combination of your continuity equation and Darcy's law. So based on your Darcy's law, and by considering your equations of continuity, what is that equations of continuity says? Whatever comes inside your soil element, whatever the amount of water that flows into your soil element has to go out of that particular soil element. That is what we call it as equations of continuity. The flow has to be continuous. Okay, so then only you say the flow is steady flow. Okay, so that equations of continuity along with what is called as your Darcy's law, we try to take into consideration. What is the Darcy's law says? Velocity is directly proportional to the hydraulic gradient, and if we try to equate that velocity and hydraulic gradient terms, we have a constant by which we equate those parameters, from which we say velocity is nothing but it is equal to k into I. So the Darcy's law, which basically says velocity is directly proportional to hydraulic gradient, from which we say v is equal to k into I. So by making use of your Darcy's law and equations of continuity, we are going to be deriving the Laplace equation for your flow problems also. Okay, so let's look at how to derive your Laplace equation or Laplace equation of continuity for this particular flow problem. Okay, what you have here basically is, okay, let's say this is my soil, this is some sheet pile, here is some water body on the upstream, whereas the water body on the downstream might be somewhere till here. Okay, so what is going to happen? Water tries to flow through the bottom of the sheet pile, that too through the cross section of the soil strata, something like this. From upstream to downstream, water tries to flow. Now, in the process, when the water is trying to flow from upstream to downstream, what I am just trying to consider here is, I am just taking a small soil element here, and I am just trying to understand how is the flow happening through that particular soil element. Okay, with what velocity the water particle is entering into the soil element in horizontal direction as well as in vertical direction, because as the flow is going to be a two-dimensional flow, you cannot say always the flow happens only in horizontal or vertical. So water particles into that particular chosen soil element can move into that chosen soil element either in the horizontal direction or either in the vertical direction. So with whatever velocity the water particle is entering into the soil element, so as the flow has to be continuous, the water particle is obviously coming out on the downstream side, but there could be a variation, a small variation in terms of the velocity with which it is entering in and with which it is coming out. Why is that velocity with which the water particle entering into the soil element is different from that of the velocity with which it is coming out of the soil element? Means in some case, water particle might be entering horizontally, but in the process, the process of your interconnected void path, that water particle may not exactly come in the horizontal, come out of the soil element only in the horizontal direction. So sometimes it might even take the z directional path to get dissipated out of that soil element. So in that sense, with whatever velocity your water particle enters into the soil element, either in the x direction or in the z direction, so with same velocity, you may not exactly see the water particle coming out. There might be a small variation in that velocities, both in x direction as well as in z direction, when the water particle is trying to leave or come out of your chosen small soil element, for understanding how is that flow happening through that small element. Okay, so let's come back to look at that small element, what we were trying to talk about. So let's say that chosen small element has got some width dx in x direction, width dz in the z direction, and perpendicular to this, okay, so the dimension in this direction we consider, let's say, it to be a unit dimension for every 1 unit in the direction, or rather I can also say, let's say, dy is the dimension in the other direction, that is in the y-axis direction, the dimension of the chosen small element, as I'm saying small soil element, so let us consider it to be dy. And we understood that the flow is not happening in the y direction because the length of that particular soil in the y direction is relatively extended to a longer distance. Okay, so first let us try to understand what is the rate with which the flow is entering into the soil element in x direction and in the z direction, and with what flow rate the water particle is coming out of the soil element both in x direction as well as in z direction. And accordingly, let us try to write down your equations of equilibrium, and from which we'll try to derive what is the corresponding Laplace equation that we can look after in finding out the solution. Okay, so here is the soil element, what we were trying to talk about. We are saying that the velocity with which, okay, so before I start talking about your velocity, what is that I am trying to talk about? I am trying to understand what is the rate with which, that's nothing but small q. Okay, so what is the rate with which the flow is happening into the soil element? With what rate the flow is entering into the soil element, both in x direction as well as in the z direction, I'll try to understand. And with what rate the flow is coming out of the soil element, both in x direction as well as in the z direction, I'll try to find out. And then we'll try to write down the equation, continuity equations, and accordingly we'll try to derive what is our Laplace equation for this flow condition. Okay, so once we say the flow rate, how do we write down the flow rate? Q is what we write it as. Flow rate is nothing but velocity into the cross-sectional area through which the flow is entering into the soil element. Okay, so with what velocity the water particle is entering into the soil element in x direction, which I'm calling it as, let's say, velocity with which the flow is entering into the soil element is what I'm considering it as Vx, and with what velocity that particular water particle is expected to be leaving your soil element is nothing but Vx plus small variation in the velocity. I said I have already discussed about why is that variation in the velocity coming into picture. Okay, there could be a small variation because of that distance traveled by the water particle in that chosen small soil element. So there could be a small variation in the velocity. Okay, so accordingly we are trying to represent that small variation dou Vx by dou x into dx. What does this dx mean? Why is that dx is represented? Because the variation for the flow happening in x direction, there is a subsequent variation in the velocity happening in the x direction. So that length over which the water particle has traveled, for that subsequent variation, dou x dx basically are considered to be cancelling out, so which simply indicates that a small variation in velocity is existing when the water particle is getting dissipated out of the soil element when it is leaving in x direction. In similar way, if I say Vz is the velocity with which the water particle is entering into the soil element in z direction, and Vz plus dou Vz by dou z into dz is going to be the velocity with which the water particle is going to be coming out of the soil element. Okay, and what is the cross-sectional area? Because if I want to calculate the flow rate, velocity is something what I have understood. With what velocity the water is considered to be entering into the element, with what velocity the water is expected to be leaving out of your soil element, we have understood. Now, what is the cross-sectional area through which the water particle is entering into the soil element? If the water particle is traveling in the x direction, then what is the cross-sectional area that is available through which the water particle is entering in? When I say flow is in x direction, then the perpendicular, the flow is always considered to be perpendicular to the cross-section of the soil element. So what is the cross-sectional dimensions here? dy in the, dz in the vertical direction and dy in this direction. So the cross-sectional area of the soil element through which the flow is entering in x direction is nothing but dy into dz is the cross-sectional area of the soil element. So that's the reason why you could see the rate with which the flow is entering into the soil element in x direction is nothing but velocity is Vx into the cross-sectional area with which the flow is entering into the soil element in x direction is nothing but dz in vertical direction, dy in the y direction. And with what velocity it is leaving out? Vx plus dou Vx by dou x into dx is the velocity with which it is coming out into the cross-sectional area through which the water particle is leaving out is nothing but once again dz into dy. And in the similar way, in z direction, if I am trying to understand what is the rate with which the flow is entering into the soil element in z direction, what is the rate with which the water particle is coming out of the soil element in the z direction. With what rate the flow is entering into the soil element in z direction means velocity is vz, and what is this cross-sectional area available? Dx into dy. Okay, so dx into dy is the cross-sectional area. What is available for water particle to enter into the soil element in the z direction, and the rate of flow with which the water particle is coming out of your soil element in the z direction. So it's nothing but Vz plus dou Vz by dou Z is the velocity with which the water particle is coming out of the soil element into the cross-sectional area with which it is coming out. That's nothing but dx in the x direction, dy in the y direction. Okay, so the same things are represented here. Q indicates the flow rate into the element, into the chosen soil element. So with what flow rate the water particle is entering means the velocity into the cross-sectional area. This I am trying to talk in the case of a horizontal directional flow. And in the case of your vertical directional flow, so it's nothing but Vz into dx into dy. Already I have talked about what are those, how are we getting it. And when the water particle is leaving or moving out of the soil element, so with what rate of flow it is coming out of the soil element in x direction and in z direction. This is all what I have already talked about. Next is the total rate of flow happening through the soil element. Whatever might be the rate of flow with which it is entering into the soil element both in x direction and y direction. So combination of this should be satisfying the condition, the rate with which the flow is going to be coming out of your soil element. Okay, so if I am trying to look at a particular soil element and if I consider that there should not be any change in volume of the soil element happening, then when only I can say what is called as a steady state flow with which the seepage is taking place through the soil. So in such case, the subsequent condition of your continuity function which we need to be satisfying is total rate of flow happening into the soil element should be equal to the total rate of flow coming out of your soil element. I am not talking particularly in a direction. So rather into the element is equal to out from the element. Whatever amount of water seeps into the element, that same amount of water has to be coming out of the soil element. May not be only in one direction, rather in a combination of x as well as in z direction. So in such case, if the total rate of inflow is equal to the total rate of outflow, then only we can say that the flow condition what we are looking at is nothing but a steady state flow. So if total rate of inflow, what is the total rate of inflow means? The rate of inflow happening into the soil element both in x direction plus z direction. So this should be equated to the total rate of outflow both happening in x direction as well as in your z direction. So what I can do for total for understanding what is the total rate of inflow and outflow, if I want to write down that expression, so what we'll have there is total rate of inflow means this term plus first term plus second term. So what I'll be getting is Vx into dz into dy plus Vz into dx into dy is going to be a total rate of inflow into the soil element, which should be equated to total rate of outflow both in your x direction as well as in z direction. So this two terms plus these two terms, I will be adding them and equating them. So if I am going to add these two terms and equate it to the addition of these two terms, so what I will be getting is this is Vx into dz into dy, Vx into dz into dy, both on left side and right side we have got, both of them will get cancelled. Vz into dx dy, Vz into dx dy, this term also will be getting cancelled out. So what I'll still have is dou Vx by dou x into dx dz dy plus dou Vz by dou z into dz dx dy. In the sense, I can simply write this particular expression. What is going to be ultimately remaining is dou Vx by dou x plus dou Vz by dou z this all I can have dx, dy, dz common, and that has to be equated to 0. What does dx, dy, dz mean? Dx into dy into dz mean? It's nothing but it is the volume of your chosen soil element. As we said, the soil is incompressible, rigid in nature. So there is no change in volume of the soil happening. So it means dx into dy into dz cannot be 0. So what has to be 0 automatically? Okay. So as this product, as this cannot be 0, so what has to be 0 means ultimately dou vx by dou x plus dou vz by dou z has to be equal to 0. That is what we have represented here. Okay, so dou vx by dou x plus dou vz by dou z has to be equal to 0 is what we are trying to get from this continuity equation. And what does vx means? It's a velocity in the x direction. Vz means velocity in the z direction. Now, how do we write down velocity equation from the Darcy's law? We have seen velocity is nothing but k into y. If I am trying to talk about the velocity in x direction, then I will be writing it as coefficient of permeability in x direction into the hydraulic gradient in x direction. What does this hydraulic gradient in x direction means? The total head difference by the corresponding flow happening in x direction. Okay, so which we can write it as dou h by dou x as what is called as your hydraulic gradient in x direction. Similarly, dou h by dou z, because your total head difference is having some variation because of the flow happening in z direction. That is what we are calling it as your hydraulic gradient in z direction. So velocity in x direction is nothing but coefficient of permeability of the soil in x direction into the corresponding ix value, where ix is what we can represent as dou x by dou h by dou x. The total head loss for the corresponding flow happening in x direction. Total head loss for the corresponding flow happening in z direction, which we will be considering it as your hydraulic gradient corresponding to z directional flow. So velocity in z direction is nothing but kz into iz. So I am going to be simply replacing from this in this equation of continuity, that is dou vx by dou x plus dou vz by dou z is equal to 0. In this vx, if I replace it with what is called as kx into dou h by dou x, vz, which I am going to be replacing it as kz into dou h by dou z. Okay. So here is that I am trying to look at dou by dou x of kx into dou h by dou x plus dou by dou z of kz into dou h by dou z. This has to be equal to 0. Okay, and if I consider the soil to be isotropic, if I consider or if I assume soil is isotropic, what does that soil isotropic means? At a particular position in the soil, at any point in the soil, the properties of the soil in any of the direction, at a point in any direction, the property of the soil is going to be same. So which property am I trying to look at here? It is the property corresponding to the flow. So which is nothing but coefficient of permeability of the soil at a point both in x direction as well as in z direction is what is that I am assuming it to be same. I am assuming that the soil, if it is isotropic, then the coefficient of permeability of the soil both in x direction as well as in z direction is going to be same. Is it guaranteed that soil has to be isotropic, sir? It is not compulsory that the soil has to be isotropic. To be more specific, in reality, soil is never isotropic. Rather, it is anisotropic. But for our life to be simple, or for making our life little simple, or for making our problems more easier, so what we are assuming is soil is isotropic in the sense your coefficient of permeability of the soil in this case in x direction as well as in the z direction is same. If the coefficient of permeability of the soil both in x direction and in z direction is same, then I can take out that kx and kz as simply, I can replace kx and kz as simply k, and I can take out that out of your differential function, because derivative of your constant is going to be 0. So from the variable separable from mathematics, if you are going to be doing that, so what I'll be getting there is simply k into dou by dou x of dou h by dou x plus k into dou by dou z of dou h by dou z, this should be equal to 0. So from this further, if I take k common, I can simply write it as dou square h by dou x square plus dou square h by dou z square. This total should be equal to 0. As the coefficient of permeability of the soil cannot be equal to 0, then what has to be equal to 0 is dou square h by dou x square plus dou square h by dou z square should be equal to 0. That is what is represented here, and which we are calling it as your Laplace equation for the steady state flow condition. So based on equations of continuity and by making use of what is called as Darcy's law, we were trying to get this Laplace equation for the flow governing problems. Now our objective is to look at how to solve that Laplace equation. So once we solve the Laplace equation, then we'll be getting the solution for how is the flow happening from upstream to downstream, what is the flow condition, what is the way how the flow is happening, is all that quantity of seepage or the rate of flow, how much pore or how much seepage pressures are existing. The problems related to all these cases can be solved out by solving this Laplace equation what we have got here. So in the process of solving this Laplace equation, we have got different solutions available by which I can get the solution for that particular Laplace equation what I have earlier given or whatever earlier we have talked about. So what was our Laplace equation that we have got? Del square h dou square h by dou x square plus dou square h by dou z square. This is nothing but simply equal to 0. So the solution for this particular Laplace equation we can try to get either based on what is called as analytical methods or numerical methods or different hydraulic models which are very much ready-made available, are based on electric analogy. Because of the temperature, because of the difference in the current flow conditions, we will be able to understand the amount of flow, or by based on what is called as graphical approach. Okay, so we are not going to be dealing with any of these different approaches which are mentioned above. We will not be looking at all these which are mentioned here above. So we will be, as of this course is concerned, all the above cases will also give the solution to your problem. It's not that we don't get the solution to your problem based on the various other approaches like analytical methods or numerical methods or hydraulic models or electrical analogy model. So we will get the solution. It's not that we will not get the solution, but however, as of this course is concerned, our main focus would be on what is called as your graphical approach. And in this graphical approach also, we have got n number of varieties of graphical approaches available based on some models which are developed, are based on finite element methods, are based on finite different methods which are available. So based on that also we'll get the solution. Basically, in this graphical method, what we try to do is we draw what is called as a flow net diagram. We try to construct what is called as a flow net diagram. Now, how do we construct this flow net diagram? Flow net diagram can be constructed by based on some of the models which are very much already developed. Prototype models are developed. So based on that, we can try to construct your flow net diagram, are based on finite element methods, are based on what is called as your finite difference methods also. We can try to construct your flow net diagram. But however, we are going to be looking at only based on what is called as your trial and error sketching approach. Okay. So based on the trial and error sketching approach only, we are going to be constructing your flow net diagram. So based on the construction of the flow net diagram, after constructing the flow net diagram, based on the flow net diagram, we will try to estimate how much is the quantity of rate, or how much is the quantity of seepage happening, or how much quantity of rate with which the flow is happening. All that we can try to calculate. The analytical methods are exact, but however they are complicated, and solutions are available only for simple boundary conditions. Because whenever you talk about any mathematical equations for finding out the solution, you require certain boundary conditions like initial and other boundary conditions to solve that particular problem. Okay. So analytical methods will give you the exact solution, but however they are going to be complicated, and it's going to be a time-consuming process. And they are therefore they are less practical, as they are relatively complicated in analyzing and solving. So they are less practical, but however they are going to be more accurate. Those approaches are going to be giving you the result which are going to be more accurate. Numerical methods, they are widely developed in the presence of now the present era of digital computers. So we have got different software packages which are available, based on which we can even try to find out the solution for that particular seepage related problems. And graphical method, which is termed as what is called as a flow net. Okay, so this flow net is something what is very commonly used, very much preferred because of its easiness and simple approach by which we get the solution. So the flow net diagram is what is that we are going to be getting it by what is called as a graphical approach. Okay, based on drawing it on a graph sheet, we try to draw that the flow net diagram. Okay, so in this particular course, as of this course is concerned, we will be limiting ourselves in constructing the flow net diagram based on what is called as your trial and error sketching. So based on what is called as trial and error sketching approach, we are going to be constructing your flow net diagram. Okay, so this trial and error sketching, how do we do, sir? Can I draw my lines as my own, as per my own convenience? Means no. There are certain procedures which have to be followed, and based on that particular procedure only, you are required to construct your flow net diagram. By constructing the flow net, we can know the values of head at any point in the soil, and also we can try to find out the flow. If you are required to find out what is the total head, or maybe your pressure head at different points within that particular soil mass, so you can try to find out our amount of seepage pressure. If you want to find out, still you can find out that. And are the amount of flow happening from one point to the other point within that soil medium? Yes, we can find out. So all that we can try to find out from this simple flow net, whatever we are going to be constructing. So generally, whenever we are going to be looking at this flow net diagram, what does basically a flow net diagram mean? Okay, so as it is a simple graphical approach, so flow net diagram is a simple way of representing the flow condition, or the way how the flow is expected to be happening from upstream to downstream. Okay, I'll stop our discussion for today here. And in the next class, we'll continue our discussion. The flow net diagram, what are the conditions that are to be satisfied with respect to the flow net diagram, and how does that flow net diagram, how is that we need to be constructing the flow net diagram? So all that we'll try to talk